Every large language from GPT to LLaMA is built from one simple repeating unit, the transformer block. It is the cell that started an AI revolution. But what exactly happens inside it? Why does stacking these blocks make models so powerful? Today, we are going to open it up layer by layer and see how exactly a transformer thinks. In the last episode, we learned how self-attention works, how each word can look at every other word to understand the context. But attention alone is not enough. We also need a way to process that information, to transform it, mix it, and pass it forward. That is where the transformer block comes in. It's not just attention, it is full processing pipeline for meaning. The goal was to design one reusable layer, a layer that could take embeddings at context through attention, and then reason over it with simple neural operation. The team behind attention is all you need did exactly that. A clean modular architecture that scales simply by stacking more blocks together. Each block acts like a mini brain, receiving information, attending, transforming, and outputting richer representations. Every transformer block has two main parts. Multi-head self-attention captures relationships between tokens. Feed-forward network, however, processes and transforms that contextual information. And wrapping around both of them, residual connections and layer normalization. Together, these four elements form the beating heart of every LLM. We've already seen attention, where each token becomes a weighted blend of others based on the similarity between queries and keys. Inside the transformer block, this attention mechanism is the first sublayer. It takes the input embeddings, compute Q, K, and V using learned matrices, and produces the contextual output. As you can see in the screen, this output represents how every token now understands the other around it. But that's just the start. Right after attention, we apply something called add and norm. Here is the idea. Neural networks learn better when each layer's output doesn't drift too far from its input. So instead of replacing the input, we add attention output back to it, a residual connection basically. Then we apply layer normalization to stabilize training and prevent exploding or vanishing activations. This ensures each block learns small meaningful refinements, not chaotic transformations. Now the model has context, but it still needs to process that information non-linearly, basically to detect deeper patterns and abstractions. That's the job of the feed-forward network. It is a simple two-layer network net. In modern models like GPT-3 or LLaMA, ReLU is replaced by GeLU or SUI-GLU, the activations that perform better in high-dimensional text space. You can think of this layer as a feature refiner. It takes what attention discovered and sharpens it to higher level meaning. In the next step, just like before, we add the residual connection and normalize it again. So we have the formula like this. Now we have a balanced and stable output, which is rich in context and clean in scale, and also it's ready to pass to the next transformer block. That's the beauty of this design. Every block enhances understanding without breaking the flow of information. Stack 12, 24, even 100 of these, and you get a deep transformer model. It is capable of reasoning, summarizing, coding, or even writing poetry. But why not just make it deeper, as far as we want? In theory, more layers mean more intelligence, but in practice, deeper models are harder to train. That is why residuals, normalization, and scaled attention aren't optional. They make deep stacking possible without collapse. Without them, your model would simply diverge. Each transformer block learns a different skill. For example, early layers learn local grammar. Middle layers learn abstract meaning. Deep layers, however, they handle the reasoning and they're specialized in certain tasks. Stack them together and meaning flows upward, from word to sentences to idea. That is how a network of simple operations turns into something that feels intelligent. However, you may note something important. There are two main transformer types: encoder blocks, which is used in BERT-like models for understanding, and decoder blocks used in ChatGPT-like models for generation. You may ask, what is the key difference? Decoder blocks use casual masking, so they cannot pick at future tokens when predicting the next one. Otherwise, it's basically the same architecture, just wired for different purposes. And basically that's it. One block includes attention, feed-forward, add, and normalization, repeated again and again. It's modular, elegant, scalable. And it's the reason every modern LLM from GPT to LLaMA shares the same DNA. These blocks aren't just code. They are the architecture of understanding itself. When you want to perform different experiments or visualize those blocks, I would suggest to go to this link. You can easily choose which model that you want to see, and you see the transformer blocks for this specific model, and you can visualize it and check exactly what each layer is doing. It is an interesting tool to check out. Now we've built the foundation, our model can read, attend, normalize, and reason. But how do we make it learn? How do we train it to predict the next word? And how can we turn all this architecture into intelligence? That is what we will explore next. How LLMs learn through loss functions, optimization, and next token prediction. And that's basically the core of how transformers come to life. If you like this episode specifically, don't forget to smash the like below and share your experience with others about your journey of learning LLMs in the comment down below. Until the next video, good morning, good afternoon, and good evening. Bye.